Here we have the standard circular model and the corresponding graph. The circle has radius A. We have an angle theta. We assume that we start at the rightmost point where the graph meets the horizontal axis, the level of the horizontal axis, as it moves counterclockwise. The angle is going to be theta, and we'll interpret theta in a minute. But if this angle theta of the point that moves around the circle, the angular position theta, if the angular position is theta, then we're going to say that the graph we have here is the graph of y equals a sine theta. Now, actually we have t for the axis here. If theta equals omega t, where omega is our angular frequency in radians per second, then our interpretation of this is that we have a graph of a sine theta versus clock time t. And the a sine theta function really is representing a sine of omega t. Theta can also be related to the position x along a wave. If this is a snapshot of a wave traveling down a string, or a wave in the ocean as seen from a side view, then we might have x instead of t here, where x represents our position along the wave. As the position along the wave changes, we're going to think of theta on our reference circle changing. And the relationship we're going to use there is theta equals kx. So rather than changing in time, theta could change with respect to position x. The constant k is called the wave number. And in that case, a sine theta would be a sine of kx. Now looking at the sines of some angles, there are certain angles for which we can determine the sine exactly. One of those angles is theta equals pi over 6 or 30 degrees, as indicated here as the central angle of this sector of the circle. Now, a sine pi over 6 is just the y-coordinate of this point, as we've seen. And we're saying here that a sine pi over 6 is a over 2. We'll see in a minute why that's equal to a over 2, why this y-coordinate has to be a over 2 for this angle. But let's accept for a moment that it is. Then we see that a sine pi over 6 is a over 2, so that the sine of pi over 6 is 1/2, as we obtained by dividing both sides here by a. Now to see why this y here is a over 2, which means it's 1/2 of the radius of the circle, let's look at this figure here. Now instead of pi over 6, I'm going to use 30 degrees just because we're more used to thinking of triangles in terms of degrees. So we have a 30-degree angle here and a 60-degree angle here. This angle is 90 degrees because, of course, here we're projecting vertically to the x-axis, which gives us a right angle here or here. Now if we take one of these triangles and flip it upside down and put it in this position right next to the first one, then we have two 30-degree angles here, which makes a 60-degree angle, and of course we have 60-degree angles here, so we have an equilateral triangle. This side is A, this side is A, because each of these sides is nothing but the radius of the circle, so this side has to be A. Now since these triangles are identical, this distance and this distance are identical, so each of these distances from here to here and from here to here is half of A. So this side is 1/2 of A. But of course this side is just y. So that's why we say that y equals a over 2, and how we get sine of pi over 6 equals 1/2. We can do a similar thing for our 45-degree angle, our angle pi over 4. Okay, for that angle we draw the same type of a triangle. It's a right triangle, so we draw it over here. Since this angle is 45 degrees, this angle is 45 degrees, which makes this an isosceles triangle. And the side then, the common value of these two sides we're going to say is s. So this side is s and this side is s, and this s of course equals y. By the Pythagorean theorem, the square of this plus the square of this equals the square of this, and we've indicated that here. A squared equals s squared plus s squared. we can solve this easily for s. We take the square root of both sides. We get a is the square root of s squared plus s squared, which is the square root of 2s squared. So that a is going to be the square root of 2s, and s is the reciprocal of the square root of 2 times a. Now we see that y, which equals a sine pi over 4, has to equal s, which is 1 over the square root of 2 times a. So we have a sine pi over 4 equals 1 over square root of 2 times a. Dividing out the a, we get sine pi over 4 equals 1 over the square root of 2. We multiply numerator and denominator by the square root of 2, and we get the square root of 2 over 2. That has an approximate value of about 0.71. We now list the values of sine theta. As theta goes from 0 to pi over 2. Now we know the exact values of all these angles, but here we're listing decimal approximations. The sine of 0, as we know, is 0. The sine of pi over 2, we know, is 1. And those are exact values, of course. The sine of pi over 6 is 1/2, and that's an exact value, so the 0.5 is exact here. The sine of pi over 4 is the square root of 2 over 2, which is approximately 0.71. That's not an exact value. Square root of 3 over 2 is exact. 0.71 is a decimal approximation. Pi over 3 is has a sine of 0.87, and we haven't seen that. We'll look at that maybe later. But we can get that by the Pythagorean theorem and the fact that the sine of pi over 6 is 0.5. And that's pretty easy to do, actually. Now over here, we've sketched a y versus theta graph for theta from 0 to pi over 2. Specifically, giving the signs of pi over 6, pi over 4, pi over 3, pi over 2, and of course 0. Now from pi over 4, or from 0 to pi over 2, the angles pi over 6 and pi over 3 split this angle into 3 equal segments, so that from here to here, from here to here, and from here to here should be equal distances. I think this one maybe has been exaggerated a little bit in my drawing. But you should understand why these three, we're just counting by pi over 6. This is pi over 6, 2 pi over 6, 3 pi over 6 essentially. And they have to be equally spaced. Of course, pi over 4 is halfway between 0 and pi over 2. We've drawn the horizontal projections of the points corresponding to the angles 0, pi over 3, pi over 6, pi over 4, pi over 3, and pi over 2. Pi over 2 on a circle of radius 1, the y-coordinate is of course 1. At 0, the y-coordinate is of course 0. At the angle pi over 6, the y-coordinate, as we've seen, is 0.5 or 1/2. So the y-coordinate here is 1/2, and we draw a dotted line at y equals 1/2. We draw a line at y equals 0.71, corresponding to the pi over 3 or the pi over 4 angle, and at 0.87, square root of 3 over 2 for the pi over 3 angle. Then we locate the points: pi over 6, 0.5, pi over 4, 0.71, pi over 3, 0.87, pi over 2, 1, of course 0, 0. We draw the curve, and we see the graph.